Okay, so let's begin. Because we are still waiting for some students, let me briefly describe what we will be teaching today in this class. Okay, so the first is that we left behind from I think 35 in the last lecture. I think because of spring break, there have been 2 weeks of time. So I will recap a little bit. I move forward. I move backward maybe a few slides to go back to the initial question, so that initial problem, so that you can know what we are talking about. You can get the context. Okay. So the second part is that we will release assignment 1 today. Okay, which is about image annotation. Right. So for simple problems like whether you can have classification, given label, regression. These annotations are simple, right? You can have a CSV file where one particular column is a label. Okay. So, but we have more complicated problems like object detection, and we will look at how we can annotate objects using a software called the Vgg Image Annotator, or in shorthand notation called a VIA. We will go through that today, and then we will go through the next slide, which is about Bayesian inference. Okay, Bayesian decision theory. Okay, so because Bayesian is a very important concept in machine learning. Okay, so at least before deep learning, right? So now deep learning is kind of just say that you just use deep learning modules and let it learn the weights. Okay, you use like Foley layer, all those layers are already predefined. Okay, before that, actually we have our own graphic model design, and then using Bayesian inference, we will estimate the parameters. Okay, all right. I think what's the time now? Let me see. Okay, it's already 3 minutes past 5. Let's begin. Right. So we can talk about some side note while most students are joining. Okay, so let me see. So last time we talked about this scikit-learn earlier, right? So which is actually a library where you can call a model, right? So let me give an example. For example, for logistic regression, our second hands-on tutorial will be using scikit-learn. Okay, if you use machine learning, you definitely need to use some library. Otherwise, it would take forever. Okay, and scikit-learn is probably the most popular library. I know that people are using like a Weka, all kinds of other data mining libraries before, but because of the data science, the Python, the Python era, right? So basically everything is in Python, right? So it's like a monopoly. So the old tools are no longer popular, and those tools in Python actually are written, a lot of them are in C. Okay, so they are very fast. Let me see. So logistic regression, although the name is regression, okay, it's actually classification, so don't be confused. Okay, so actually it's a regression of the probability that for a binary classification problem, what's the probability that your class has label 1 instead of 0, right? So it's basically a classification. It's larger than 0.5%. You think it's positive, otherwise it's negative. Okay, but you can actually go a little bit beyond that. We will probably expand beyond what we will be talking about today, and we will take a look at those concepts, like the AUC curve, right? So, and the ROC curve and AUC. Okay, and yeah, let's take a look at how you can use logistic regression model. Okay, so it's very simple. In Python, you say, hey, from this package where you have a bunch of linear models, I want to use logistic regression model. Okay, and once you import this, right? So then what you do is very simple. You say, hey, because I already import this class can be the right use. Okay, if you just import scikit-learn, you say scikit-learn.linear model.logistic regression. It doesn't matter what it is. You just know that it's a model that does binary classification. Okay, so y is either 1 or 0. Okay, x is the features. So all you need to do, as we said, is that you say, hey, this object equal to this model, right? So in Java, we need a new, right? In Python, we don't need, okay? It's basically create the object, okay? And then using this class. And then we say fit, right? We get the training data, right? And we will also talk about how or why we need this, right? So we will have the concept of training data and the test data, and we need to split, okay? there's also a concept of validation data. Okay, here test data is 0.3 means training data should be 70% and test data should be 30%. Okay, so we will look at those concepts shortly. Right. So, and there are also a bunch of packages that in scikit-learn you might want to know. One is metrics, which gives all kinds of metrics. We will see that shortly. If I forgot, just remind me. Okay, and yeah, so logistic regression, basically, if you call the fit, then you can predict, right? Then the Y is a prediction, okay? So which will be either the probabilities or the class labels, okay? Whether it's binary classification 0 or 1. Okay? And a very important thing that we probably have gone through last time is, let me see, this is page 31. Okay. So let's go to a previous page. Last time we talked about overfitting, right? So when we talk about overfitting, we have seen this thing, okay? We have seen this part, right? So this part is called L2 normalization, okay? Because the W is a vector, W, it's a polynomial function, W0, W1, all the way to Wn, okay? And if you forget, you can go back to the previous slide. Let me see how.
Professor, can you please explain the difference between the L1 regularization and L2 regularization? Can you just give us a brief?
Yeah, I will do that shortly. Just a minute. Let me find the annotation tool because yeah, I cannot use the annotation tool here when playing slides. Otherwise, it will be a conflict. So let me. So this is called L2 regularization. Okay, there's also L1, LP regularization. Okay, so what are these concepts? So basically, they are defined on the norm. Okay, called LP norm. Okay, of vector. So it's like if you have a value, right, in scalar, it's a one value. Right? So for a vector, you have so-called a norm. Okay, and for matrix, you have P norm. Right? So for vector, it's called LP norm. Okay. And you also have like a Frobenius norm. I think we have seen some of those earlier. Right? So this is basically 2 norm. Right? So basically, you think about this is W. Okay, we have a bunch of values. This is 2 norm. Okay, L2 norm. It's not 2 norm. Okay? Although the name is a little bit. Right. So if you look at LP norm, so this is LP norm. Okay, so this is the shape. Right. So if you have 3 norm, L3 norm, then it's a cubic, and 1 by cubic. Okay. So basically, it will be take square root 3, right? So the x1 absolute value, okay, cubic plus all the way. So I try to use this because it's a little bit faster. But if you have difficulty understanding my handwriting, okay, just let me know. Right? I will use the latex pen. Okay.
It is good, Professor. I think I understood the LP norm. Can you please explain, like, where do we use L1 and where do we use L2? Like, which
okay. Yeah,
example?
I will do that shortly. Okay. So yeah, so keep it in mind that LP norm has absolute value. Right? For quadratic, you don't need absolute value because quadratic is always positive. Okay, but actually it all has absolute value. Right? So if you look at L1 norm, right? So these are just a 1. Okay, so it's absolute value plus. Okay, and this is just 1 by 1. So you don't have it. So this is called L1 norm. Right? So this is L1 norm, L2 norm. Okay, and if you have L is the other very popular norm is called the L infinity norm. Okay, L infinity norm basically takes the maximum value of norm. Right, so because norm is always positive, you take absolute value. This is like a Manhattan distance, right? So for L1 norm, okay, it's like if you are here, it's like x plus y. Okay, so for L1, right? So if this is all 1, okay, and if this is the it's a maximum y. So because you can consider if you have a particular xk is maximum. Okay, you can divide everything by xk. Okay, I'm omitting the absolute value. Okay, but you actually have the absolute value already. Okay, right, and you know that xk is the maximum element among here, right? So basically, all the others will be less than 1. Okay, only one term, which is k, will be 1. And now we take the p into infinity, right? So these, if you know that something like 0.6 less than 1, right, to the power n, if n goes to infinity, this thing goes to 0. Okay. So the other terms are just go to 0. Okay, only this term will go to 1. Okay, so basically when you take p to infinity, this term is 1, which means this thing equal to this thing, xk is the maximum, okay, which gives us this conclusion. Right, so this is all infinity now, which is the maximum.
So Professor, here x1, x2 are the weights or the values, like the values of the attributes?
So here is a vector norm. Okay, so we are talking about just a vector. It's okay? The vector can be a weight. It can be the input. It's okay?
Okay.
Yeah, we are talking about what is the LP norm, right? So now let's go back to our model. Okay, so just to remind you of where we were. I cannot use this here because that will cause a lot of trouble. So we are talking about x is just one value, y is t. Okay, so here the w is really w0, the weight matrices. Okay, right. So if you remember, always keep in mind, supervised machine learning is always learning something like if theta x. Okay, so we are talking about theta right now. Okay, normalization, regularization is always on theta. Okay, when you talk about model, not on x. X is a constant. Right, so yeah, so this is on the theta. Okay, this is the model. But Tn and the xn are what you see. Right. So similarly, there's another model called Logistic Regression, has similar form as polynomial, but we don't want to expand to that. Right? So actually it's a linear model, right? But with some logistic function. We will describe it later in a later lecture. Okay, but keep in mind it's something similar, right? So it has an internal parameter. For example, in here you can see they have some attributes, right? They have the coefficient, like those. This is a ax plus b speed, right? So basically it's a line. Okay, so this is a linear model. Right? So basically they have some parameter which when you call fit, you are training this model, right? And they also have they have the model parameters which you are optimizing. When you call fit, it's optimizing. These are actually hyperparameters. Okay, so this C is what? For example, if you look at logistic regression, this C is exactly the lambda here. Okay, it's the regularization factor. Okay, and by default it's 1. Okay, because we have seen, right? So lambda at most lambda data. Usually it's smaller than. Okay, sometimes in certain cases you want to use a bigger lambda, but it's very rare because you don't want to put too much effort on the regularization. Otherwise, you will have a flattened line because all you care about is just make it 0. Right? So okay. So this is C is basically the lambda, right? So so another important thing, penalty L2. Okay. So basically they are saying they are using L2, something like this. Okay. So because this is a linear model, the W is just ax plus b plus A and B. Okay, that's the W. And if you look at the penalty can be changed to L1, can be changed to L2, can be changed to none, which basically remove this term or reset lambda to 0. Okay, and there's also a concept called elastnet we will talk about shortly. Okay, we can see. Okay. And the other. So there's also class balance issue, right? So we will talk about in the next slide. Okay, in the next PPT. Okay, in the next lecture. Okay, and let me see here. So you can see some terminology like C before the 0, right? So this is what? This is regularization factor. Okay, right? So all you can do is this is actually inverse of regularization net, which means the actual inverse of that. Right? So you can read the tutorial, the API, and what's the input, what's the output, and you can use it. Right? You don't even care about what's happening there. All you do is provide X train, Y train, and fit. Okay, get the model. Right? So this is second one. Right? Okay, so yeah. By the way, last than that, we'll take a look at the last thing. Okay. So ElasticNet is another regularization. Basically, find a middle ground. Okay, find a middle ground between L1 norm, which is here, and L2 norm. Okay, L2 norm is also called a ridge regression. Okay, or Tikhonov regression. Okay, just make them fancy. And this L1 norm is called a lasso. Okay, exactly this way. Okay, so if you look at some like machine learning papers, say some ElasticNet or ridge or lasso, it's just these things. Right? Whether you use this is ridge, this is lasso. ElasticNet is say, hey, I have both, but I have a weight tuned, lambda 1, lambda 2. Okay, so that's nothing special. Okay, when you see something called lasso, it's just okay. So also remember, these are the weight parameters that you are trained when you call fit. Okay, and finally, why we need the L1 and the L2, right? So what's the difference here? Right, L2 is typically what you will stick with. Okay, let's go back to the previous example. L2 is what you. This is different, right? So this is a loss function. Okay, it's not, but we can see some trend here, right? If you have this green bar, one is very far away from your desirable value, right? If you square it, okay, this one will be dominated. 100 square will be 10,000, right? Other small value square doesn't play a part. Okay, this is similar. Okay, if you have a regularization, right? If a particular number is very big, then that's really bad, right? So you actually try to avoid those overfitting numbers. Okay, but it will not try to make some number 0. There's no sparsity. Okay, if you use L1 norm, okay, which means you don't have the square, right? You have the L1 norm 1 here. Okay, what will happen is that you are trying to specify the model, which means, for example, ultimately you say, hey, I only have this term, and this term. Instead of n plus 1 terms, I only have 3 or 4 terms. Right? So this is actually using support vector machine. Okay, there's also other kind of regularization. We will see all kinds of them later. So just to get the concept. And again, what's the purpose of regularization? Anyone can tell me what's the purpose of regularization?
To avoid overfitting?
Yeah, avoid overfitting. Okay, avoid this. Okay, so I think that's pretty much the side note, and we have enough students coming. So let's go back to the real estate. Okay. Yeah, we will catch up from what we left behind last time. So here we are looking at example for classification, right? And so the task is to learn the class of a family car, right? So we have 2 labels. One is family car. Let's say we can make it 1. We have a negative class, which is other cars, a sports car or a private car, right? So so we have 2 attributes here, right? So x1 is price, x2 is engine power, okay? And our y is output label is a class, whether it's family car or not family. Okay, come back to our model here. So x is engine power and price. Y is the family car not. It's a label, right? And we have some theta we want. Okay. All right. So usually we will use this mass calligraphy notation for the training set or for the data set. We have n examples. Each example is x and y. Okay, x is a vector, which means x1, x2. Y is just a label, right? So whether it's family car, right? And L means the else data. Okay, so because we have so many data, it's a set. Okay, and you may see some people don't use the parentheses. Okay, that's not professional. Okay, for professional machine learning people, okay, they all use parentheses because otherwise you can mean it's to the power of L, right? So it's to the power of k, it's square, cubic, this kind, right? So usually for the number, so for the ith data item in the data set, right, we use parentheses. Right? Okay. And so, yeah, for each data item, we can write x1 is here, x2 is here, then it's a negative class. It's not a family class. So we can plot a dot. Okay. And there are only 2 features for simplicity. And now class label is 1 is a family class, 0 is not a family. Right. In this diagram, always keep in mind when we plot the feature space, right? So the feature space does not include y, because y is something in another dimension, right? So this is plus or minus because it's a classification problem. Okay. Here we will assume, we will have some hypothesis. Okay, we will see this later. Okay, we will assume a shape of the model, just like before. Let's say the original curve is sine, right? But we assume it's actually polynomial, right? Maybe it's not absolutely correct, but the model will be useful if we use like order 3 polynomial. Okay, so here we assume it's actually a rectangle, right? So it's an axis aligned rectangle, right? So we assume it's of this shape, right? So because we know that, for example, x1 is price. If you want a family car, it cannot be too cheap. Otherwise, it's too dangerous, right? You have so many people in the car. Right? If there's a crash and everyone dies, it's not good, right? So, and the other is, it will not be too expensive, right? It's family affordable, right? It's not a luxury. Okay, so this is why we assume there will be a range, but we don't really know what's the range of P1 and P2. Okay, so on the other dimension, engine power, right? So obviously, if you have a family car, it cannot be, the power should be large enough for a family, right? So, but you will not need a sports car, right? If it's too strong, it's really for speed, then it's really not for the purpose. Or it's a truck, right? So it's different. Okay. And so we assume there's a range on each dimension, which gives you a rectangle, right? But we don't really know the parameter E1, E2, and P1, P2. Here, E1, E2, P1, P2 are the theta here that we try to do that. Okay, when we try. Okay, so this is model, or we also call it a hypothesis, right? And it's defined by 4 parameters. Like this f function, we have theta, which are the
I want to play 5 minutes of home.
David, you have any question? If not, let's continue. Right, so if you are, if you have a question, just unmute yourself and ask. If you don't have a question, just mute yourself. Okay. And so next is remember, hypothesis is just a model. Okay, it's just another name of model. Okay, so model are what, for example, in scikit-learn we have logistic regression, maybe some deep learning model, etc. Okay, support vector machine. Okay, so a learning algorithm finds a hypothesis to approximate the class C. Okay, and so we have a ground truth class. Okay, we will see that later. Okay, and we want our hypothesis to be as close as to the class. Right. So for example, in our previous regression example, because we are talking about classification, in the regression example, hypothesis is polynomial, not sign. Right? The true class is sign. Okay, and so here, for example, our hypothesis is a function f, right? And the theta is already hidden there, right? So we give a particular theta, we have a particular model, trend model hypothesis. Okay, and here you can see that the hypothesis or the model gives 2 labels, right? 1 is positive, and 0 is negative. Okay, and the hypothesis, or we say the model, is uniquely defined by a parameter theta of 4 values. Right? The low end of the price, high end of the price, low end of the engine power, high end of the engine power. Okay, and so we need the hypothesis class to be as close as C, which is the class used. Okay, so let's say assume the true class. The true class may not be a rectangle, by the way. It can be a circle, right? Or any ellipse. That's any shape. Okay, but let's assume that true class is also a rectangle, something like this. Okay, that's a true class if your engine power is within this range, E1, E2, and your price is within this range. Then any point falling here is a family. This is the C, the true class. Okay, but you don't know it, right? So what we will do is we will draw another rectangle, like H here, okay, with another set of parameters theta. Okay, and you want the H to be as close as C, right? But you don't know whether it will be as close as C, by the way. So because if you look at this H, it well separates the positive class with the negative class. Right? There's no error. Okay, if you look at C, it's the same. Okay, so you never know whether because based on the data you see, you don't know the underlying class is C. Right? But you want to try to close the gap. So unlike regression, where we have the sum of squared error we see before, right? In classification, we usually use accuracy. Accuracy means something like, for example, if you have x1, y1 in the test set, okay, where the data you never see, x2, y2, okay? and x3 plus 3. Okay, then you give the model h here. Okay, and you see y1 hat, which is the prediction. You see whether they are equal. Okay, y2 hat, whether equal, whether they're equal. If they are equal, then you are correct. You get a score 1. Okay, if they are not equal, you get a score 0. Right. So this is accuracy. Right. So 1 minus accuracy is called error. Right. If they are not equal, then you contribute 1 to that. Okay. Otherwise, it's so this is a total number. Right. Usually you can divide by n, then it becomes accuracy or the error rate. Okay. This is error, and you divide by n, it becomes error rate. Okay. Accuracy is 1 minus error rate, or you put this equal. Then it's accuracy. So you can see one key information we want to see is that it doesn't care about whether it's positive or negative class, right? If the true class is 0, you are also predicting 0. Or if it's 1 and you're also predicting 1, then you are correct. Your accuracy will increase. Okay. Otherwise, if this is 0, or you assume it's 1, or this is 0, you assume this is 1, then you make an error. Okay, contribute 1 to the error. Okay. So this is more like a exclusive OR operation, like bit operation. Right. So keep that in mind. Okay, this is accuracy or error rate. Okay, and then sometimes we do care about the class. Right. So for example, if you have patients like cancer patients and normal patients, people like control. Okay, let me see. Sorry, I'm using a tool that so I cannot use this. Let me use this. Sometimes I will lose control. So now, for example, if let's say we really care about positive class of cancer patients, whether we predict cancer patients correctly, right? If some non-cancer patients, we predict cancer by some fine-tuning, we can filter it out. Okay, so there are sometimes we do care about positive class or negative, which class you belong to, for the true side and for the predicted side. Right? So we will look at some of the concepts later. Okay? Now you can see there are some mistakes, right? So you can segment this space into 4 parts. One is the gray parts where both are correct, right? So you think it's positive, and the hypothesis is also positive. You have the white part, which is both are negative. Okay. You have also this rectangle and this rectangle, right? For these 2 spaces, you assume they're positive because it's in your H hypothesis rectangle. Okay. But the actual label are actually outside the C, the ground truth, so they are actually fake, right? So they are false. Okay. So you are thinking your model predicts them as positive, but it's a false positive. It's not actually positive. Actually, it's negative. Okay. So this is called a false positive. Right. So this may be type 1 error or something. Right. So there's another. I don't remember which one is type 1 error, which one is type 2 error, but these are errors. Okay. This is the reverse. Right. So actually, this is a positive class. Right. It's within C, but it's outside of your box. Okay, you predict it's negative, but it's a wrong prediction. Right? It's actually positive, so it's called a false negative. Right? So these positive or negative, it's according to your prediction, and this false or true is according to the ground truth. Okay, this is how you know. Oh, so actually maybe. Yeah. So there's also terminology like let me see. So I forgot which one is which one. Okay, basically, it's the same thing. Type 1 error is false positive. Okay, right. Type 2 error is false negative. Okay, so if you forget, you just Google, right? Because 1 and 2 doesn't mean nothing, right? So don't get confused. So these terminology are kind of like in statistics people they want to use it, right? So it's like a barrier that we try to remove those terminology barriers. Okay, hope you understand. And again, let's go back to this rectangle model, and let's say these are the negative samples, and these are the positive samples, right? If you want to make no mistakes, all 3 boxes here, the brown one, the gray one, and the light gray one, they all make no mistake because inside it, you contain all the positive samples. Outside the box, you contain all the negative samples, right? So actually, if you look at S, it's tight on each side, right? If it's a rectangle. Okay, so this is called the tightest rectangle. This is the most specific hypothesis, right? So I'm strict, right? Only in this small rectangle I think it's poly, right? And we can also have a most general hypothesis, like the brown rectangle, okay? Which means, hey, I almost hit every boundary to the negative sample. If I go beyond, I will have some negative sample mistakenly predict as positive, right? Okay, and I can also find a middle ground in between, right? Let's see. Okay, so which one will be better? Who can tell me?
Most specific, most general will be better hypothesis.
Not really. So both are very bad. Okay, for example, yeah, for example, if you go bypass a little bit, you make a mistake. Okay, if you go bypass a little bit, you make a mistake. This is very sensitive. Okay, usually you will find the middle ground. Okay, so somewhere. I think I'm using the wrong here. Let me try it here.
But Professor, if we are taking the most specific hypothesis, are we like, are we not concising the date, model to the exact data?
No, actually, both are fine, but let me try to, no, so the story is like this. So if you assume this model, when you see those positive negative samples, the safest choice is in the middle ground, okay, so somewhere here, okay? I don't know why there's some delay. So let me try to plot it again. Half on each side, okay? So that's a rectangle, right? So this is safe choice because if you shrink or enlarge it a little bit, you will not make any mistake. If you are very close to the boundary of positive and negative sample, if you shift a little bit, it will be totally wrong sometimes, right? So positive will just go negative, and negative will go positive, right? It's not a stable model, okay? But there's not much theory here right now, and we will see some like the margin concept in support vector machine later, okay? So right now, you just think about all those rectangles are bad, okay?
So,
yeah.
Can you say it's domain specific, like if false positive or false negative is what's more critical to my model? Should I make it most specific hypothesis or more general?
Here,
Right.
by the way, here we don't have any false positive, false negative. It's okay. You see, there are no points here, right? For example, if we do have a point located here, then this point becomes false negative. If a point is located here, then it's false negative. Now, actually, these two dark gray rectangles are empty, which means there's no false positive, false negative. It's okay. The accuracy is 1, error is 0. Latif, is this okay?
Yes.
Yeah. So we don't have that thing yet. Here, all of them are 100% correct. Okay. It's just whether it's generalized or not. Because, for example, it's totally possible. You can imagine maybe these samples are too few. Right? Maybe next time you will see some plus here. Okay. But if you use the most specific one, you will classify it negative. So it's not safe. You better put it in the middle. Okay. Because you only see a limited number of points. Do I answer your question, Latif?
Yes.
Okay, then let's move on. Okay, so there's actually a concept called version space, right? So because rectangle is simple, right? Maybe you will have more complicated assumptions than rectangle. Okay, so the version space are basically saying that if you make a equally good assumption, right? So which means you are all correct, right? So you can have all rectangles in between these S and G, right? Most specific, most general. You can have any rectangle, any left edge between here and the top edge between here, right? It's always valid. Okay. So yeah, let's take a look. Okay. So this is because you are using a rectangle. Okay. So if you have a rectangle, but you have something like exclusive OR shape. Okay. So let me give you an example. Let me use the right tool. Okay. For example, if you have plus, and a minus here, right at the corner, okay? Actually, you can do that, right? You can use a rectangle to do that, okay? So that looks Okay, but if you want to use the axis aligned rectangle, like use this axis line, okay, parallel to the axis, it's kind of difficult, right? So unless you have a little bit shift, if it's exactly like this, then it's very difficult, right? So if you have an axis line, it's difficult to do that, okay? And again, the best model for the previous example is actually something like this. So it's not axis line, okay? It's better you have something like this. In between them, it's nice, okay? So this probably is a safer model, right? But you cannot do that using rectangle if you are exactly axis line, okay? But as long as you shift a little bit, okay? So for example, these 2 points, okay? These 2 points are not exactly axis line, right? You have some on X, you have some on Y, okay? So then actually we can prove this nice, so basically you don't assume that the coordinate is all the same. If there happen to be some coordinate the same, you add a very, very small epsilon, let's say 10 to the power of -6, right, to break this assumption, okay? As some random shifting, okay? Very small shifting. Then if in that case, you can show that you can always shatter endpoints if you use a rectangle, if that number of points is 4, okay? But if you have plus, plus here, okay? You have minus, minus here, right? So this rectangle is the value, okay? This rectangle, okay? On the other hand, so you can get any combination, right? So if we assume this is positive, and this is positive, okay? And this is negative, right? And then we can find some rectangle like this, okay? Yeah, we can shatter, okay? So for any combination of positive and negative assigned to the data point, so your X is fixed, right? X1, X2. Y, you can get any combination. And a rectangle can always separate them, okay? If there's only 4 points, right? So we will talk about it in the next slide, okay? So here is a concept of model complexity. We call it the VC dimension, okay? Again, this is only of theory value, okay? In reality, we don't really use it, but it's kind of getting you understand the the concept. Okay, there's a branch of machine learning called a learning theory or machine learning theory. It's super theoretical, okay, and may just give some hints to real life, okay, but may not be directly useful, okay. And there's a company called the NIPS, right now called the NIPS, okay, and which is for this kind of paper, right? A lot of paper out there, okay. And so here, if you give any point label, right, whether positive or negative, randomly give, right? So how many combinations are there, right? So there are 2 to the power of n combinations, because for the first point, you have 2 possibilities, this 2 possibilities, this 2 possibilities, this 2 possibilities. Then there are 2 to the power of 4 possibilities in this game, okay? And for any combination of the label to those x points, x are fixed, by the way, but you can give any label, right? Your model, let's say a rectangle, can always shatter endpoints. Shatter means positive samples are on one side and negative samples are on the other side, right? If you can make no mistake, then you can say that your VC dimension is 4. Okay, so VC dimension maximum number of points that can be shattered by it, right? We can show that if you add another point, 5/5 points, okay, then this is not true. Okay, there's some certain positive negative combinations that the rectangle can never separate them. Example is very simple. Right? So if you have, I'm using it wrong. Okay. Let me use name. Right. If you get some positive here, negative here, and then you add another point here, or you give it a positive, right? Then there's no way to plot a rectangle because there's a bar here which is negative. Right? So any rectangle will cross this bar. Right? So if you want to say, hey, internal is positive, then you have something negative. Okay. So you can easily show that. But the difficult thing is to show that if you have 4 or less points, then you can always shatter them. Right? So there's a proof here. If you have interest, we can go if you are a serial people. Okay? So in this case, less than 4 or equal to 4, we can shatter them. Beyond 4, we have counter example, we cannot shatter. Then we say the VC dimension is 4. Right? Only 4 points, we can totally shatter. Okay? So VC dimension, if it's larger than your model expressiveness is not, right? But actually, this is a toy example. In reality, VC dimension is very difficult to compute. So it's only of series value, okay, to help you illustrate the concept. On the other hand, let's say if you have this model positive and in between negative and this positive, right? If you have a circle, right? So a little bit more complicated, right? Outside the circle is positive, inside it's negative. Then you can do that, right? So let me see. So rectangle can also do that, right? But you can construct an example where rectangle cannot do that, right? So my previous assumption is that, but you can make examples. For example, if you have something like a positive, let me see, positive here, and negative on this side, then potentially you cannot find a rectangle to do that, right? So yeah, I think there's no rectangle you can handle. Okay, my previous example is wrong, okay, because you can plot the rectangle inside it. Okay, but if you want the inside to be positive, it's difficult, right? Because if you have positive on both sides, then that's still valid. Okay. Any questions so far?
Yes, Professor. So the VC dimension is used to measure the, let's say, the accuracy of the model, that how much it can shatter data points.
It's a complexity model, right? It's more like the polynomial. If it's a linear or quadratic or cubic or ordinary, okay, it's a complexity model, right?
Okay.
Yeah, because for example, in our previous example, but again, it's only of zero value. Okay, right, so n equal to 9. You can say it's very expressive, right? VC dimension high, right? Because it can hit every point exactly. If you use a line, there's no way to do that. Okay, this is of course in the regression case, which is difficult to illustrate, but it's a concept. It's a model complexity, how expressive model is, right, to your data. Okay, your data can be super complicated. It's not a linear model. You cannot separate them, right? So you need a more complex model. But complex model will overfit. Right? You don't have so many data. The model itself has more points, like ordinary parameters more than the data, right? Then you want to prevent overfitting. That's why you add the regularization. Is this okay?
Yes, sir. Thank you.
Professor, like the VC dimension that we are using to identify the best model, or I mean, a model complexity in sense, like are we comparing models or just
So maybe I didn't make it clear. So the VC dimension is a metric for how complex the model is. Okay. Is this okay?
I'm just trying to understand, because the version space actually consists of multiple hypotheses, right? So are we trying to?
No. So
Okay.
basically, for any points, it can be any location 4. Okay, it can be different combination 4. If then you give any of the labeling method, you can always separate them. Then you say the VC dimension is at least this one. Okay, right? So this is following the definition. But again, as I said, for complicated functions, for function not in the rectangle, it's a complicated app, right? You usually cannot compute the VC dimension really, right? So it's not so useful. It's just telling you that the metric to evaluate the model complexity. Is okay?
Yes, Professor. And what else? What other techniques do we use to calculate the model complexity?
You don't really need. In reality, we don't compute the complexity because you immediately know, right? For example, for the polynomial, okay, you know that order 9 is more complex than order 3.
Okay, Professor, got it.
A simple way is really see how many parameters you have, right? So if you have more parameters, like W1, W0 to W9, it's more complicated. It's a more expressive, of course, than W0 to W3. Is it okay?
Yeah.
So there's
Thank
some empirical method. So machine learning is kind of theory combined with empirical. Okay, you see those people tuning parameters. Right? So, okay. All right. So now let's talk about the model complexity. Okay, it's actually sometimes you don't want to use too complex models. Sometimes the simple models will be preferred. So the reason for that is because your data could have noise. Okay, so there are different kinds of noise. The first is measurement error. Right? So for example, if you have a GPS coordinate of your location, let's say longitude, latitude, let's say x1, x2. Okay, it may not be accurate. Right? So you know it's for your navigation system. Right? So for Google Maps, for example, sometimes if the signal not very good, right? So is there no base station to correct the GPS coordinates, right? So you will see yourself if you are driving along the sea, right? So you will see your car is driving in the sea, right? So it's measurement error, okay? Second is labor, right? So it's annotation, right? So that's why we want to tell you emphasize the importance of the assignment one, right? If you give garbage annotation, right? So if you label it randomly, right? So then you learn nothing, okay? For example, if someone tells you, hey, label that data, okay? If you label one data item, I give you $1, right? So all you want to do is you want to earn more money. Then you just label randomly, right? Plus, minus, plus, minus. This is the fastest to earn money, right? It has no one to really cross-check whether your label is correct. But that's not good, right? Oftentimes the noise is not from that, it's from human mistakes, carelessness, right? So, or some bias, okay? Sometimes you want to cross-sourcing because some people think this is positive, some think this is negative, right? Or like a medical imaging, right? So you see this guy is in trouble, right? Have cancer. That one, since he's still okay, keep observing, right? So sometimes it's more subjective, okay? And there's also possibility that you do not have the important feature in your X, right? Maybe you have X1, X2, X3, a vector, right? But somehow you are not aware of X3, right? You only have X1, X2. X2, X2 is actually not the key dominant factor of Y, right? If you miss that X3, then you can think about noise, right? Because you don't have that in your variable, okay? In your system. It becomes a noise. Now let's take a look at this example again, right? The family car example. But let's consider the special case where we have, let's say we assume this H1 is our model hypothesis, right? But unfortunately, this is not 100% accurate because for the positive class space, the gray space, you have a negative class inside, okay? On the negative class, right, so we have a positive class inside. So we have two mistakes, right? Accuracy -2, error is 2, okay? But we can make a more complex model, right? So let's say this curve, right? Then if you want to represent it, it's very difficult, right? So how to represent it? Maybe piecewise linear or some other method, okay? Multiple curves pieced together, right? Spline curve, okay? So then you will have way more parameters than E1, E2, P1, P2, okay? Is this preferred? Because this model makes no mistake, right? Any idea? Which model will be preferred? Who can tell me?
Simple one.
Simple.
Which one?
Simple.
Simple one, right? So yeah, so we will prefer the simple rectangle. Okay, this is because almost all of them are properly shuttered. Only some of them, right? But this could be because of human error, right? Relabeling error. Okay, this is actually positive. Okay, right? And there could be a measurement error. Let's say this point GPS location is actually you are detect here, but you actually here, right? So that could be measurement error, right? So usually we will prefer the simple model. Okay? If you just make a small amount of mistake, okay? Instead of using a complex model to tune to this noise, right? If you have this cut out, this is because of the wrong label, right? But your model changed a lot because of the wrong label, right? So this is not a stable one, okay? And this is actually not the ground truth. So we prefer simple models because it's of course simpler, right? So computation is faster, okay? And secondly, your spaces, training space is lower, right? Because you only have theta is only 4 numbers. Right? For this, you may have 100 numbers. Okay? And it's also easier to explain, right? When you talk to people, hey, if your car price is within this range, in the meanwhile your engine power is within that range, then it's a family car, right? If you want to explain this curve to some people, it will take some while, okay? Right. And finally, it has better generalization, right? So this is called outcome gradient, okay? Right, for example, let's assume your actual label for this plus is here, okay? But somehow maybe some measurement error is shifted here, okay? Right, but generalization means you want to predict unseen label. Let's say you have another point X and Y here, right? You want to predict its label. It's most likely negative, okay? But you will predict it's positive if you use this complex model, right? This is because your model is tuned to the noise, right? This dig out, right? So this is because you learn the noise basically, okay, right? So you learn the error, okay? And this do not generalize. A lot of the negative labels are labeled positive in this code, okay? This is not good. So you want a better generalization, and there's also some tool to measure that using variance. Right? So your variance should be low.
Hi,
Yeah.
doctor.
Yeah.
Yeah, I have confusion about the noise. Can you tell something about the noise? What is the role of noise here?
A noise can be annotation error, right? So we talk about three noise. Just one when I lose control of my. Yeah. Okay. Let me try to do this. Let me clear this for you. This is noise. Okay.
Mm-hmm.
Yeah. So there's a measurement error. Let's say your actual point is here, but you shifted the say x2, right?
Mm-hmm.
A little bit. You come here, right? Okay. This is one noise. Another labeling noise. Maybe this is positive. Someone say it's negative, right? Okay.
Mm-hmm. Mm-hmm.
Any questions?
Okay.
Yeah. So because of these small errors, you make your model complicated.
What's the difference between noise and error? That
Here it's a thing because we don't want to use error. Error can also mean the model error, right? So prediction error. Let's say you have a y, and you also have a y hat, right? So this could be the prediction is actually y hat, right? Right? So and you have a true y, right? So there's a difference between y and y hat, right? So this is also called no, this is also called error, right? So this is yeah. So we want to differentiate, right? So here our error is no, it's not this error. Right? This error is how your prediction is far from your ground truth. Okay. Right?
okay.
You choose theta to close the gap. Right? Well, this error, this noise here means it's inherent to x and y. It's nothing really to do with model. Okay. Whatever model you use, you have this error.
Okay. Right? Thank you.
Data error. Okay. It's not a model error. And now, so far, we have seen a family car not, right? A binary classification, okay? We also have the case where we have multiple classes, right? So if I give you an image, you tell me whether this is the sports car, electric car, or family car, right? So there are more than two classes. How can we define this? Right? And so there are models directly learn K-class, right? So, but there are also models that the model itself is designed for two-class. Okay, like support vector machine, you have a one line separating two space. Okay, or we say hyperplane separating two space. Okay, one side is positive, one side negative. In that case, for support vector machine, if you have K-class problem, it will have to transform this problem into two-class classification. Okay, but we haven't covered what is SVM yet, right? So here in this course, we really need to go fundamental because a lot of students don't have the concept. Right? We go a lot of advanced stuff, but yeah, you just feel confused and it's not helpful, okay? So we will really talk about the basic stuff until the very end where we will really move faster a little bit because we want the final product to be more advanced, okay? Here, for example, we go back to our previous example where each rectangle represents a binary classification problem. Inside rectangle is positive, outside is negative, right? Then in that case, you can say, hey, sports car is inside this rectangle, right? Luxury car is inside this rectangle, okay? And a family car is inside this rectangle. That's just, if you consider two-class classification problem, there's actually some confusion, right? What if my car is here? Is it a sports car or a luxury car, right? So this is the question, okay? And what if a car is outside, right? So it's closer to family car, but it could also be a sports car, who knows, right? So maybe expand this, it's smaller, expand this larger, who knows, right? So how do we give the label for them, okay? Yeah. The only thing that I'm pretty sure is if it's this triangle, right? Inside this rectangle, but not inside the other rectangle. It must be electric, right? But how do we define these? Right? So this we need a discriminant function. We will talk about this later, okay? And let me see. Yeah. Next is another example, right? So previously we talked about classification. Next, let's look at a regression, right? Again, we have those data, but the difference is that y is no longer labeled 0 or 1. It's a continuous number. Let's say the temperature or the price of the car. And so yeah, so it's a real number. Okay. And in regression, we usually assume it's of this shape, right? It's a prediction of x plus epsilon, right? Epsilon is the n random noise, right? So why we need epsilon? Again, it's for the same reason. It's data noise, right? You can have these errors, okay? One typical reason we always add epsilon because maybe we have some xk that is not observed, so we are not including into x. So that actually is it, right? So it will impact you. But because you don't see it, you never know whether for a particular x it's a positive impact to y or negative impact to y. You model it as a random noise. Let's say Gaussian distribution with a very small variance. Okay? And you really want to learn this mapping from x to y. Okay? So again, this f has a parameter theta, right? So it's this f. Okay? So how do we measure the error? Right? So the error, empirical error, is measured in this way, right? So this is a real number, this is a true label, okay? So this is y hat and y, okay? And here what we do is we actually consider a square, okay? And then we sum up. This is called the sum of squared error, okay? Here we have to use rectangle because zoom is a little bit more powerful. So this is sum of squared error you see before, right? And then we take the mean, right? So this is the average squared error. If you take a square root of it, right? So if we take a square root of it, then this is root mean squared, okay? So this is all for regression, not for classification, okay? So this is error. So this is model error, okay? Because we have the model f, okay? So the error is with model, noise is with data. Any questions here?
Professor, can we call epsilon the bias? Because that looks similar to the bias. I mean, I'm just...
No, bias is always along one side. Epsilon is random, okay? Right. When you bias, you hold a positive view or you hold a negative view. It's a system error, okay? Epsilon is sometimes it's positive, sometimes another x you're back. It's a random error.
Okay, Professor. Thank you.
It's just something you don't know, but it's impacting one, okay? Maybe some human mistakes, some hidden factor. All right, so let me ask you this question. Right, so for regression, we have this mean square error. Okay, so this is mean square error. Okay, right. So for classification, what's the error? Who can answer me? For classification, right, we don't have this continuous number. What's the error?
Sum of number of wrongly predicted labels.
Yeah, so it's this one. Right, so I think we have that. Oh no, here. Okay, right.
Yes, that's it. That's one.
So this is called error. Okay, for classification, what you want to minimize. Okay. But this is a little bit tricky because you cannot, it's a not continuous thing. Right? You cannot take gradient. We will see way to handle that. Right? Softmax, sigmoid function, for logistic regression. We'll see that later. Okay. But this is actually once your model is trained, it's your classification model. Right. So this is always a metric for evaluating your model performance. Right. So this is called error. And if you divide by n, this is error rate. Let's say in 100 samples, 80 of them are correct. Right? So it's accuracy 80%, error rate is 20%. It's the error rate. Okay. Error rate without divide by. Okay. Yeah, this is for classification. Regression, a typical error is this mean square. Okay. Yeah, this is regression. Okay. And we want to find an f that minimizes error. Okay. Minimize the epsilon here, right? Hidden here. Okay. So yeah, so it's kind of we want to minimize. Okay. And this epsilon is actually in this YL, right? This observed label. All right, so polynomials, for example, if you want to fit this line, right? So I think a line works pretty well already, okay? And if you use second order, it's fine, right? So it's a curve. If your range is really just this range, it's probably okay, okay? It's a better fitting, okay? But if you say, hey, I want my model to be super complex, sixth order, right? Then it becomes some kind of shape like this, right? So this causes trouble, okay? Why? Because, for example, your mileage is a little bit longer, you drive your car a little bit longer, what's the price? The precisely you expect something at a point here, okay? Right. But if you use this 6th order, it's a very, very small price. It's a free, basically. It's negative, right? It's not derived. If you drive your car for a long time and when you sell it, it will not be negative. Okay, so any questions? Okay, let's continue. So learning itself is an ill-posed problem, right? So data alone is not sufficient to find a unique solution, right? So you have to assume the model. Let's say it's a rectangle, it's a circle, right? It's a 2nd order, it's a cubic polynomial function, or it's a nice order. Okay, so this is where the bias is. Right? You have the inductive bias, the assumption about the model. Right? I just think this should be order 6 polynomial. Right? So if you think of order 6 polynomial, you have the bias, but that's a bad bias, right? So because of model error, right? If you think a 2nd order, this is okay, right? So this is pretty good. So the bias is always, you know, it's your bias. It's one-sided. Okay, it's not the random noise. And bias is with model. Okay, noise is with data. Okay, this is just terminology, right? So you can also say the error is with data. Right? Okay. Error with data is just noise. Okay. So generalization, right? So we don't care about how well you fit the training data because you see all those x, y, right? It tell you x, look at the table, right? So you can put in a SQL database and do a query. You get that, right? Okay. What we care about is the data we've never seen, right? It's a long mileage, whether we are still active. It's not active. Okay. So this is called the model generalization, right? How well a learned model performs on new data not seen before. Okay, because this is a prediction model. Okay. For classification, regression, supervised learning, it's prediction. You want it to give you some new scenario, right? And you want to predict it with small error. Okay. So you want a model that generalizes. Okay. And there are 2 cases that may cause your model to perform bad, right? So poor. Okay. So for example, it does not generalize well, right? So one case is your model is more complex than your ground truth. Okay, your class C or your regression. I think I have to mute this one. Let me see how to do that. I don't know. So yeah. So I will do that shortly. Okay. So overfitting, right? So is that H is more complex than C or F. Okay. Underfitting is H is less complex than C or F. For example, if you assume the previous F should be quadratic, right? If you think it's a line, right? So it's a line. It may be underfitting, right? If you use a 6th order polynomial, it's overfitting. Okay, both are not good. The error is smallest when it's quadratic. Right? So when overfitting happens, right? If you assume your model is too complex, then that what can be achieved, right? It's overfitting. When it's underfitting, right? So if your model is, your model is too simple, right? So then you are underfitting. So this means that your model is not expressing that. And so for example, if you, let's go back to a previous example. So this zoom, you will see what I see, so it's not good. Right? So otherwise, if I use the other mode, I can easily do that. Unfortunately, you have to be able to. For example, if you think of these points as sign, right? So if you use order 3 polynomial, it's good. Right? So if you assume it's order 1, it's going to be very bad. Okay? So this is underfitting. Okay, your model is too simple. Right? This is overfitting. Okay. Yeah, let's have a try. So do you see this this slide and also something down here, or you don't see it? Who can tell me?
Yes, sir.
You see what?
Sir, we can see. I can see the slides at the
Slide
bottom.
only, right? Anything down there? Do you see that?
Yes.
You also see that?
Yes.
Yeah, that's why I cannot do that, because if we use projector, I can put here and you jump here and there. Now I have to flip back and forth because you see what I see, right? In the projector, you only see the slide. Okay, you don't see those down here and you don't see. So that's why I have to flip back and forth. Okay, apology for that. And yeah, I see a question asking me what is COF, right? So C is basically this classification problem, the ground truth. Okay, and what is F? Right, F is basically the true curve. Okay, so the ground truth curve, maybe the sine curve. Okay, so it's basically the ground truth model, the ground truth rule between x and y. H is your model, the truth model. Okay, let me see. So Harris, did I answer your question? If you want type, you can just type yes.
Yes, yes. Sir.
Oh, okay then. Yeah.
Thank you.
All right. So model selection is to choose the right inductive bias. Right? So basically, you can try. One example, you can try linear second order, third order, all the way to sixth order. You know that sixth order is already too much. You don't need to go up. Right? And then you see which one gets the least error in the test set. Okay, in the validation set actually. Okay. Which is a better choice. Okay, so then that's the good model. Right, so you need to choose inductive bias. Right. So in
Professor.
Yeah, please go ahead, Deepak.
Yeah, the yield post is only for the linear, or we can use it for non-linear also.
Which one? Which
the
one?
yield post problem.
No, yield post problem is saying the H is the yield post. Okay, you never know it's linear or quadratic or sine. It's okay.
Mm-hmm.
Learning is basically learning f theta. Okay, this is a yield post problem. It's not a linear or quadratic. It's okay.
Hi, I'm looking at the homework assignment and I'm wondering what is via?
Via basically we will cover that after break. Okay, it's a software, right? It's not. We will cover that in the second part of the lecture, right?
Oh, okay.
Yeah. Yeah. Let's finish this slide because I should have finished that earlier on before the spring break. That's a. Yeah. That's so model selection is basically saying what you select. The inductive bias has another name. Okay. Another name is called hyperparameter. Okay. But because it's not part of the optimization, it's not a part of the training. Okay, you need to give it and it's trained. Okay. Any question about this? Again, I use the wrong tool, so I lose control of my mouse. Yeah. Okay, so hyperparameter. So again, maybe you will be confused about the concept of hyperparameter parameter. Let's go back to the previous slide. I don't want to flip too many pages. It's crazy. So let's just use this mode, and let's see which slide. Okay.
So,
yeah.
I have a quick question about the elastic net and the in elastic net lambda one. I mean, we are using two regularizations, right? L1 and L2. Then the hyperparameters would be the regularization for both. I mean, there will be two hyperparameters.
Regularization, right? So yeah, regularization lambda 1, lambda 2 are hyperparameters. You need to specify them. Okay.
Okay.
Just like the C in the logistic regression. Okay.
Okay.
Yeah.
Okay. Thank you for trying to prove.
Yeah. Just one moment. So by the way, can you answer this question? Right. So here in this regression model, what is the hyperparameter? What is the parameter?
Order M
is what?
M. I mean, what is the polynomial? What big? No.
Which one is the parameter? Which one is the hyperparameter?
W is parameter and
X
M
is hyperparameter.
W is the parameter and M is the hyperparameter.
Yeah, M is a hyperparameter. Okay, so you need to specify it. It's your bias. You assume how complex the model is. Okay. Once you specify it, we have seen a note. I hope you have gone through that because you also have the spring break. Right. So we have a lot of things you need you guys to prepare initially. Right. So because of the Python basics and also these concepts. Right. So W is where you optimize. Okay, the mathematical concepts. Right? But M you should get. Okay. Once you get the M, your fit model is just training W. Okay. We can go back to the logistic regression model. Okay. So for example, here the C is the regulation parameter, right? It's a hyperparameter. Okay. You can also say these are hyperparameters. Right. Once you define the hyperparameter, your model is set. Okay. Your bias is there. Okay. Right. And then with this model, then you call fit, and you know, so right, and let me see where. Right here, this is them, right. So then you call fit and prediction, right. So here is where you give a hyperparameter, okay. Then you are fit. Fit is training the parameter theta, okay, and then theta is the step you have the predict, okay. So this is the hyperparameter in scikit-learn, and internally it has a parameter you don't know. Right? So this is the same if you look at deep learning. Right? Different layers, they have the feature kernel, right, for CN, and like the other weight matrices for dense layer. But in Keras, you never see them. Okay, it's hidden there, right? But the parameters you need to specify how many hidden units if you know what is in deep learning. Okay, and then you fit those parameters, and then once both are set, parameter have one set, the function is determined, and you predict. Okay. Any questions?
Professor, I have a question here.
Yeah.
Let's say for a simple regression, the loss function is just the mean square error, right? If we include the L1 and L2 regularization, then it would be the error will be different, right? Then can we assume that choosing the error function might be also can be a hyperparameter?
Yeah,
choosing an error function
you can assume
can
it.
also...
It's more like the inductive bias. Okay, hyperparameter is one kind of inductive. Like M is a parameter, right? But those options are more like model designs, not just the hyperparameter. But you can treat all of them as hyperparameter. Okay.
Okay. Thank
you. Usually, if it's a number or a vector or a matrix, we call it a hyperparameter. If it's like an L1 norm or L2 norm, then it's a model design. Okay.
Okay, Professor.
Yeah. And if you look at what we derived the last time, I think we have the note. Well, we computed the loss, right? So this is error. This is E is a loss, okay? And if you have a projected error, right? If you take a projected error, it will just add another term there, and all these equations will be updated, but it's still the same. It's W0 to W. Okay? It's just you can still use the same logic because we have shown that the function is convex, right? And then if you add another norm, okay, it's still convex, right? So you can still use the gradient descent, right? Because any norm is convex between them. Whether it's vector norm, matrix norm, any norm is convex. Okay, convex plus convex, still convex. Okay.
Okay, Professor. Thank you.
Welcome. And by the way, so all these gradient stuff, we will have to teach them, right? Because it's a basic code, but now people don't use them. Okay, so because the Keras TensorFlow basically do that for you, right? So this is what's a trend actually. So because I need to mention this, right? So we are teaching the basics, but if you are not good at them, you can still survive, right? So for example, let's look at the Camille Gould, a researcher in deep learning. Okay, so he published a ResNet paper in 2016, and the citation is 55,000. What does that mean? Just in 4 years, there are 55 papers published citing this paper. Right? Why suddenly so many people? If you look at these days, if you look at deep learning papers, okay, anyone can get maybe 1,000 citations if you have a reasonably simple model that people can use. Okay, this is because the models hide the gradient descent for you, but those packages do that for you. If you build on top of them, you don't need to care about the gradient optimization stuff. Okay, right? So that's why. So it's now become a toy. It's more like an algorithm design. There's no mathematics, right? So that's why it's important to learn TensorFlow, PyTorch, and Keras. Okay, unless you want to do the gradients yourself. Okay, and actually, a lot of people can have higher citations than Turing or winners, right? Because deep learning is just actually it's making things simple, not complicated. Okay, you hide the gradient stuff, but as a fundamental course, we need to teach these things, right? There are also courses using TensorFlow directly for this kind of machine learning course, right? So I don't take this option because then you don't see what's happening down there, mathematics. Okay, and there's trade-offs between three factors. Okay, so first factor is how complex the model is, whether it's order 2, order 3, or order 6. Okay. The second is the training data size, right? Whether you only have 10 data or you have 100 or 1,000. That matters a lot. Usually, if your machine learning data has less than a few hundreds, it will not train well in typical model. Okay. And generalization error. Okay. Of course, if your model is very simple, right? So then you only need maybe 20 or 50 data. You can still train. But usually in real applications, the ground truth will be complicated, right? So you need at least maybe 800 data, 2,000 data. Okay. And generalization error. So is how your model performs on the new data. So we have 3 factors. The first is how complex the model is, right? The second is how many data you have to train. Okay. The third is on the unseen data. Okay, how your error will become, right? So what you really care is this, right? The error. Okay, it's a generalization error. Right? How your model predicts on unseen data. Okay, but these are what you have to make decision, right? How complex the model should be, right? And how many data you have. This really matters, right? For machine learning, it's called a data-driven method, right? Because all you do is put the x1, y1, x2, y2, x3, y3, all the way 1,000 of them, for example, how many data you have, right? And let them learn the theta itself, right? And f is your assumption, okay? Usually not so complicated. It's a general function. Even in deep learning, it's the same. It's whether it's a fully connected layer or the recurrent neural network, the convolution. Is you have a fixed f, okay? And then you learn theta, which is the parameters, this module. Okay? And then here are some relations, right? If your n increases, your error, generalization error, will always decrease. That means the more data you have, the better. Okay, so the model will always train better. We have seen example before. Let's take a look at it. It's let me see. It's here, right? If you only have 9, maybe 10 points data, right? If you assume a complex model, your data is not enough, right? Your model will be not generalizing well, right? But for the same order 9, okay? It's a yeah, maybe look at this example, right? Both of them are order 9, okay? But now you have more data. This curve is a little better. This is way better. Okay, so the data also matters. Okay, it's actually a degree of freedom kind of thing. But just get an impression of this because the first lecture is really about multi-side machine. Okay, the second thing is a little bit more complicated, right? So how do you choose a model, right? The model, if you make it more and more complicated from a very simple model, initially the error will drop. This is because you're underfitting, right? So your model is not complex enough to express the data points you have, right? The shape is not right. Okay. Now, if your shape is you can capture, if you make your shape more and more complex, then it's overfitting, right? When it's overfit, the error then rises. Okay. Initially drop and then rises. Okay. So it's something like this. Okay. Initially drop and rises. And here is where you will select your model complexity. Okay. This is the right place. And how low you can get at the lowest point. That depends on how much noise your data have. So the data quality is really important. Right? You see a lot of the data pre-processing, cleansing, this kind of thing. Right? If your data is noisy or garbage, then you learn nothing. Okay? And there's also a concept of cross-validation, right? So let's say all the data you see right now, we can call them the training data. Later, your unseen data is called a test data, right? But when you do experiments, probably you want to hold out some data to be test data, okay? Okay? That's the trend test split we see in the previous secular code, if you still remember. But now, if I only have this training data, I want to choose model, right? Whether it's order 1, order 2, order 6, right? How do we do that? What we'll do, we will hold out some data for validation, because this is validation data, okay? Then we train our model here and then see how it performs here, right? So this basically gives you an estimate of the generalization error, right? And then we try maybe second order and try and see the error, third order, try the error. And we pick the lowest error one, okay? Maybe it's a quadratic function instead of others, okay? So in this way, you can actually select your model bias or hyperparameter, okay? So keep in mind, validation data is to choose model choice, model selection, or what do we select? We select the right hyperparameter. Okay, this is what we are doing. Okay, train is to find the best parameter and this hyperparameter setting. But given different hyperparameter setting, we'll have different errors. And when we choose a hyperparameter, we do cross validation. Okay, let me clear this. Yeah. Right, so this is validation set. Right. Cross validation finds the hypothesis most accurate on validation set. Right, so you want to split the data where most of the data will be training. Right, so because training eats a lot of data, it's data-driven method. Okay, then you want to choose model selection. Right, so if your validation set is too small, only 1 or 2 points. Right, your variance is big. Right, maybe the randomness will cause a lot of error. Right, so the best model you choose is not so good. Right? But as long as your validation set is reasonably large, maybe 100 data. That's good enough, okay? For the test set, it's really evaluating how, so now I choose the second order. Right now I test how this model performs on NC data. Okay? So usually we'll split into 3 data sets. And resampling is needed when data is limited. Okay, so because if you only have 100 data, but you want to train a lot of them, right? So you have to resample it again and again. But there's a concept of data corruption. Let's say if you sample a data into training set, also in the test set, right? Then the test set will be high because you already see that data in the training set. Right? It's tuned, minimize the error in the training set, which also the data you see in the test set, right? So this is called data corruption. Really, for machine learning, we do want the data to be abundant. Okay, there's few shot learning, this kind of concept. Right? So few shot learning. Right? So which means you see a little bit of data and you want to learn it. Right? So this is, there's no free lunch. Okay, you want to have so-called transfer learning. Okay, this is another branch of machine. Okay, so you already have another model that is trained by a lot of data. Okay, and that captures the hidden rules. Then now you have a little bit of the data you have. Right, so here you have a small amount of data. Right, so for your target problem, you change a little bit to the soft level to target label, and you fine tune a little bit because the model almost trained. Right, the features are good quality. Right, and now you transfer most of the knowledge here. Then like already have a background of data. Right, then you use some small sample of data to fine tune your model to your target problem. Right, so there's no free lunch. You always need a large amount of data. Whether it's transferred from a pre-trained model, right, and then you do fine tune, or you have some other method. Okay, but you always need some, you always need some solution. Okay, there are also some solution using loss function. Right? So there's some called the triple loss. Okay, so this is another example. So again, machine learning is really a loss function optimization. The triplet loss is saying that, for example, if you have a bunch of faces, right, you only see those faces, right? Now, let's say you see Obama and you want to see another face of Obama, right? So you don't have so many data, right? So for the database, you just see how close it is, okay? How close it is. Maybe to Macron, the distance are way larger than to Obama. Okay? Of course, this image, it's way complicated. You need a deep learning to extract features, okay? See convolution. But the idea is similar, right? So triple loss just say, now I just learn all the relationship instead of directly learn whether it's positive or negative, right? Whether I'm closer to Obama or to Macron, okay? So this is other way to do feature learning. But again, you still need some source that you have a lot of data. Okay? Without data, in machine learning, we have a concept called cold start problem, right? Cold start. Cold start. So that means, what is cold start? For example, in computer, if you have cold start, it means you're capturing the hot, right? So you don't know which data you will access, right? So, but in machine learning, cold start means initially we have no information about the application data you see. Right? For example, if you have a new account to YouTube, right, it will recommend some videos that are generally popular. That's learned from all the population, right? So again, they have the data to learn, right? And for you, specifically, after you watch more and more videos, right, so cache become hot, right? So they can give you better personalized recommendation. Otherwise, you have the cold start, okay? finally, we talk about 3 dimensions. First is model. How do you choose a model? It's and a theta. Okay, here we use G. Theta is like a condition. Okay. If you think about condition probability, right, theta is first defined, and then you have the observations, so generalization direction. Next is a loss function, right? So this is like the y is the y hat is the prediction. Right? The true label is what? Right? How far away is your data item different from your prediction? Okay. Usually for each data item we have a loss, and we sum them up for the whole data set. Right? So because we want the loss to be small for all the data, right? We want to minimize the sum of data. Okay. But there's some theory actually there. Okay, we will see that later using probabilistic theory. Okay, why we use that for specific models. Okay. And so finally, now we define the loss function, right? Then basically we want to find theta that minimizes. We put a theta into this function, right? We want the error to be minimized. Okay, right? So this becomes an optimization problem, right? So the target is minimize this error, and the variables is theta. Okay, so this is the optimization problem. And it's a very difficult. Right? So if you look at convex optimization, and now there's a lot of non-convex optimization. And so Stephen Boyd from Stanford, basically, if you want to do NIPS and ICML, right? So this is a basic book you need to finish reading. Okay, so so many pages, all mathematics. Okay, so it's high dimension. Okay, it's crazy. Right? So again, this course we don't require you to understand almost all of them. So some of them, like the Lagrange method, we will describe. Okay, so this is basically optimization theory. I think you at least know linear program, right? It's a very simple form of optimization. Okay. And there's a no free lunch theory. Okay, so basically you don't know which one is the best model. You try different models and you find the best one. Maybe it's different shape of the model, and maybe for the same model you also try a bunch of hyperparameters. Okay. And in scikit-learn, we do have some tool to help you find the hyperparameters for the grid search. It's a stupid way, but it's useful. Okay, in case you later want to use, you can use it. Okay, it's called a grid search cross-validation. Right? So it will do cross-validation because validation. Hyperparameter search, you need a cross-validation. Okay, validation. And here's an example. Right? So you want to try these parameters for this model. You search, right? These ranges, you want to try these ranges, okay? Or different parameters. Okay? These are hyperparameters you want to try, and it will work. Okay? I think we are pretty much over time. And the different types of model have to divide due to the nature of different data in real applications, right? So that's why besides machine learning, we also have data mining. Okay, data mining is machine learning on real applications. Okay, and the data science is on real data. Okay, right? So, and data science is also saying that we need an application. Right? So you have CS, math, and domain. Okay, so data science. If you look at data science, there are several things. The first is yes, this is data science. Right? So if you see, you need to work on a particular domain. Right? So apply to maybe medical science, social science, etc. Okay. The second image of data science is kind of Python libraries. Right? So I don't have it right now, but a lot of Python libraries. Okay. We have seen that in the first class. Okay. So data science is data mining with Python libraries. Okay. All right. So any questions? And data mining is not just machine learning. Okay. Also visualization, pre-processing, all data mining. Okay. And this finishes this slide, and we will take maybe 15-minute break, and then for the rest of 45 minutes, I will go through the assignment here, okay, and then we will start the next lecture, okay. Any question? If not, we will take a 15-minute break. We will come back in maybe 6:45. Okay, I will mute myself then. If you have a question, you can put it in the chat. I will come back and answer them. Okay, let's begin. So I will briefly go through our assignment. Oh, by the way, so if you come to the Canvas course web page, now you can see all the information. Okay, like Jalal is one of the TA, and when is his office hour, and this is a Zoom link. You can connect to him. Okay, and this thing is our second TA, and office hour on Thursday, 9 a.m. to 11 a.m. And this is the Zoom link that you can use to connect to him. Okay, this is our course link. Okay, if you log in Canvas, so you can navigate through and go to whatever Zoom link you want. Okay, any questions?
I didn't see the screen. I'm not sure if it's just the other one. I'm not sure if you're sharing the screen.
What? Latif?
Yeah, screen sharing, it is not on. Screen sharing?
Oh, sorry. Yeah. Let me, this one, let me see. Okay, yeah, so here's our course website. If you go to home, okay, and you can see every information here, like Jalal is one of the TA, and here's his office hour. This is Zoom link to connect him, okay? And this thing is our second TA, and on Thursday, okay, this is the Zoom link to connect to him, right? And if you forget the class link after logging to, login, and you will click this link, you can connect to our class, okay? Of course, there's other information, but the links works fine. And regarding the assignment, I will briefly go through the requirement of this assignment. Okay, so this is called annotation with VIA, right? So what is VIA? So the important thing about the assignment is read the content. Okay. Just one moment, I hear some noise. Let me mute all. Okay. All right, let's begin. Yeah, so because we are talking about supervised learning, right? All we see classification regression belongs to supervised learning, okay? Supervised learning basically needs supervision, right? You need to give the label annotation, okay? So we want to learn a relatively advanced annotation tool, okay? This is very important because if you look at what is machine learning, it's data driven, right? It's just y, okay, x is there, and you give y, okay? Then it learns what y should be given x. So this is a relatively more complicated one, okay? But it's still just one, right? So in this assignment, you will be asked to annotate 10 images, and you should have received the email sharing the folder with you. Okay, if not, contact Jalal. If that's still not solving the problem, just contact me. Okay, and you can use VIA. So what is VIA? VIA is a Vgg Image Annotator. Okay, so I'm not sure whether you are familiar with computer vision stuff. So in deep learning, there's called a Vgg Net, right? So it's by this group, research group called Visual Geometry Group, right? So they also develop a tool for computer vision, right? So just how to annotate the objects, okay? And the algorithm of computer vision, usually what they do is assume that anything, this is called image segmentation, right? Anything inside this polygon belongs to one object. Let's say this one, okay? And outside it not belong to this object. Every pixel inside it. So based on this principle, okay, and then you can define the class, right? And there's also a tool for video, right? So you can recognize who is who, okay, when the video is playing, right? So we will use version 2 image annotator. Okay, there's a version 3 is for audio and video. So we are not doing video or audio. Okay, just go to image 2. And the nice thing about VIA is that it's standalone. It's a JavaScript written tool. Okay, all you need to do is just download it. Okay, let me see. No, I think I should have a look at that.
I have a questions.
Yeah.
Yeah, it's annotation means do we just we have to circle or something like that, or we have to give the description?
Annotation in general means you give the one, okay? annotation gives a true one, right? Depending on the application, X and Y can have different form. Okay.
And do we need to give the description about?
No. Here our definition very simple. You give a polygon. Okay. Anything inside the polygon belongs to this object. Okay.
This is the annotation, right? This swan.
This is annotation. Okay.
Okay.
In general, annotation is just the labeling, or we say give the Y. Okay. Because we need the X and the Y to train, right? It's okay.
So we just annotate and we have to mention the class as well, or like just draw that.
You have to. This is what. So we will go step by step. You see, this is you do this and you click and you say which class is the class. Is it one? It's okay. Right.
Yeah.
Okay. So we are going through this too. It's okay. Yeah. So basically, this is VIA. If you click, you will see this file. Okay. And we do provide a VIA tutorial. Okay. So you can easily download it. Okay. And this tutorial tells you everything. Okay. But unfortunately, it's an older version. Okay. It's a VIA. I think by that time we prepared. It's not 10. It's 8. Okay. Actually, I like the old version, which is more dense. And these are the menus that you need to go through in order to understand it. Okay. And what we do is we have a transmission tower images. We have a lot of them. Okay. And we want to I will go through that shortly. Okay. So basically, we want to take the parts of it. Okay. Take the parts of it and annotate and say what it is. Okay. We will briefly go through it later. So that's main knowledge. Okay. And before starting working on this assignment, we are strongly recommended to go through this VIA tutorial. Okay. Even I don't remember how to work with it now. So you need to read it. Okay. Grades are given based on the percentage of missed objects that should be annotated. Right? So what does this mean? So maybe in this image you have multiple objects, right? 4 objects that TA thinks should be annotated. Okay. I will describe what are those things that you'd better annotate. Okay. And you annotate only, let's say you annotate only 3 of them, right? So then you get 75% for this. Okay. So this is how you get it, right? But we do adjust a little bit. If you annotate a lot, so we will try to give you some compensation, right? So maybe you instead of annotation 3 of our 4 desired objects, right, obvious objects, you annotate a lot of others, right? So what we will do is basically we have a way to calculate that. I don't remember right now. So basically, the rule is very simple. Okay? We have a formula for that, right? So how many that we think you should annotate? If you annotate, you get some. Okay, if you not, if you annotate a lot of others, right? So this will also boost to your score. Maybe you will get maybe 90 or something. Okay, 80, 85. Okay, so if you are not certain, just annotate more. Okay. And so you should receive an email, okay, today, right, containing 10 images in the folder, right? It's shared through USB box, and the Jalal should be sending. Okay, if you don't find it, the files, contact Jalal and contact me. Okay, because the time ticks from midnight tonight. Right? So, and you have the time till next Wednesday midnight. Okay, so it's 1.5 week. So basically, we allow you to pass them next Monday. If you have any question, you can have time to ask. Okay. So, and this will be a slide on, instructions of the assignment. Okay. And here's a sample image you can download, and it's sample annotation. Right. So we will look at them one by one. Okay. Let me see. Yeah, let me do it here. Okay. So for VIA, it's very simple. If you download, you decompress, and you want to use it, you just say, hey, I want a VIA. Okay. Then you can directly use it. It's just a standalone HTML file. Okay. And there's some demos which, if you're interested, you can try to see how to work with them, but it's not useful. Okay. It's just a tell you how to start it. Okay. So we will just go with the VIA without anything else. Okay. It's a clean VIA. And so And in the meanwhile, you will have a folder of a lot of images, right? So these are the images. And let's also download something else. Okay. Here we give you a sample image, right? So you can download it. And this data contributed by all of you, if you later in the final project, you decide to work on this project, right? So you can train a model to recognize objects, okay? So this data you can request from us and we will share with you as a zip file, okay? So these images are too big. Basically, we'll zip everything, including annotation and image, and we just download it and then train it, okay? If you decide to work on this project, which will be a little bit difficult, we will have other potential projects you can choose from, okay? As a semester gets to the end, we will tell you, okay? So these are the, let's say these are the nuts. This is the screwed thread, this is screw height, okay? So there's a lot of things that you can annotate. The criteria is that you don't need to annotate everything, right? This is a drone image, okay? So basically they fly a drone on this kind of transmission tower, see where the missing a part is at, right? So if you can recognize those stuff, then you just take a polygon. So usually, if you fly a drone, you can go to different angles, right? So usually, the parts that face you, right? Those parts here are important parts, right? You don't really need to care about those parts down there. It's a very high resolution. But these are on the back end, right? Maybe drone fly to the other hand, to the other side they will try to fly. Okay, so usually, if your annotation goes beyond maybe 50 or 100 objects, but definitely you are over annotated, right? But on the front face, you do want to annotate stuff like this, especially those big ones, okay? And maybe some of these are also interesting because it's on the front side, okay? And so this is the sample image. And this is a sample annotation, okay? Somehow it's directly showing the file, it's not downloading. I don't know why. So this is the camera, canvas issue. So if you go to file and find this file, and you can download it. Okay, so I think it's in the VF folder. Okay. And in order to make sure you are downloading, just click here and download. It will download. Okay. It's all in the file tile and this thing. Okay. Yeah, I think it's already here. Okay. Now, actually, you don't have to put end of the image folder. Okay, put end. So now our task is to, for example, in here, what we can do is this, okay? So firstly, you can load image, right? So you can add files, okay? You can also add from website, okay? So, but here, let's just using our example, and we know that we have a lot of images, right? So we have these 4 images, okay? These 3 are just during the break I done. Cat 1, cat 2, cat 3, cat 4, okay? So this is cat 1. Let me see why I make it so small. Somehow I think let me refresh. If we refresh, basically it's a reloading. Okay, I would say okay. So don't refresh unless you you save the other. Okay, so I think the Zoom is making something really disturbing. Yeah. So here these are the 4 images. Okay. Right. So in the meanwhile, you can also annotate annotation. Annotation can have 2 formats. One is CSV, one is JSON. Right. So maybe you will ask what is JSON. Right. So what is CSV? CSV is a comma separated file. Okay, it's very simple. It's just for example, it's just this kind of table. You can open it also in Excel. Okay, so it's just a comma separated table. Okay, so let me see why these images are of so low resolution. I believe we can have higher resolution. Yeah, so this is comma separate data, okay? This is CSV, okay? And if you look at what is JSON, this is JSON, okay? JSON is just a file to write your Python object kind of thing, right? So, you know, for example, this bracket means this is a dictionary, this is the key, this is value, right? This is the second key, this is second value. Second value itself is a dictionary, right? So you have a key person and you have a list bracket, right? So this kind of thing, okay? It's an embedded, you know, Python object. If you look at it like this, okay? So that's why it's so convenient to work with Python, right? So because when you load the JSON object, everything is just a list of dictionary, okay? And here you can, your annotation can be saved in two formats. One is CSV, one is JSON, right? So that's import CSV, okay? So remember that we have this sample annotation also for you, right? If you click this, it will load it, right? So these are the objects. Actually, we don't even require it. Here is these are the objects. And again, so then you need to read the, so this is a sample annotation for you. Okay, so this is what we are hoping you can do. Okay, I think this is. Let me see. Oh, any questions so far?
Could you reshare Jalal's email?
Jalal's email, right? So, yeah, so you are from Auburn? Yeah, so you can contact, you know, Gopi. He will handle that. Right, thank you. All right, so to read through this tutorial, okay, let's take a look at here. So let's briefly go through this. To read this first, okay, let's add a file, okay, and then you can add images to the project, right? So this is what we have gone through, okay, and then you have the file names down there, right? So, and you have the annotations also, right? So, and now we can define the object labels, okay? So if you look at here, remember each object also has a, let me see, each object also have a class, right? So here, basically, we are using this attribute, okay? Here, we can define attribute name. Here, we only have one Y. Y sometimes can be more than one, right? So you have a box, you have a class. So here is a class, okay? If you say class, add, you will add a class, okay? But inside the class, right, so what you can do is you can say, hey, for this class, what are the text I want, right? So then you can put the text field, okay? So in this example, I'm not sure whether it's missing. Yeah, so this head and this kind of thing, right? So these are actually attributes added, right? So right now it's, oh, this is a type, okay? Its type is class. Okay, you can have checkbox, okay? By default, it will assume it's a radio, okay? By default, it will assume this type is maybe I should open. Somehow this is missing. This one. Not easy found. Oh, I'm not sure why. It's a new version. Basically, this is gone. So basically, you need to define those labels. Okay. So let me do this again. Yes, Ami. I think you should mute yourself. Okay. And then import annotation. Okay. Yeah. Let's first tell you how to annotate. Okay. So the first thing you can do is you can say, hey, I want a class. Okay. And then I will have a radio. Okay. And then so for the radio, I have some choice. Right. So all I have right now is cat. Okay. So I will have a cat. Okay. And maybe I also want to add a dog. Okay. Okay. We can do something like this. Right. And then once you define these and use polygon. So this is now where you want to define quality, right? So polyline, and this is the one cat. Okay, so I see some students are making it very crude, right? So, but we do want a little bit of high quality in order for the model. Okay. And in the end of this semester, we will tell you what are the models. Okay. And after that, you click this again. You say it's cat, it's a model. Okay. And you can do this for different animals, right? So you do want some quality. So this is a cat. You can click the polygon and do this. Okay. So we let you guys do maybe not too many, right? So 10, and then you can get comfortable with this. Okay. Right. And you click enter. Okay, this is the cat. Right? Okay, this is I think this is the cat. Okay. Right. So you can also delete it. Okay. You can also delete it. So escape is deselect. Okay. And I think there's a way to start. It's all in the manual. Okay? I haven't used it for a while, so it's kind of yeah. You can select. Okay, and if you want to delete, you click delete. So there's a lot of instructions, and do read that. Okay, so for this demo, you have to zoom in, zoom out, and we also provide instructions. Maybe Control Plus or no. Yeah. So there's a way to zoom in. Maybe use this, right? So you can zoom in, and then you can annotate. Okay, you can annotate. And we do have some classes that you need to be aware of. Okay, so let's use this to describe them. Okay. So this is, oh, unfortunately, I'm not sure why it's just gone. I think the new version is not so good, or maybe because of these. Let me just try to refresh and just load the demo. Okay, see whether this problem is solved. Basically, because the cats and the other files are not in the same category. Maybe that's the issue. File. Let's just add down, and let's import annotation from Json. No, from system. So you can import, and after your annotation will be saved as another JSON file. Okay, so which is the export. Okay, you can save it as JSON or system. We will just use system. Okay, because it's like a table, like one row. Okay, so, but again, I forget the operations that the best way to work on this. Okay, so because this is a high resolution image, you need to figure out. So basically, the first thing you come in is that you choose text into radio. Okay. Oh, why? I think the new version has some problem. Maybe I will send you guys the old version. It's gonna work well. I think the new version is not compatible. Let me try an older version. If that's not compatible, I will put an old version and send it. Because they have a new version 10, right? So let me just put an old version here. It's the same basically. If you open it and you add the file. And then you add annotation. Import. And then you can by the way, you should choose this to radio. Yeah, then it's already there. I don't know why the new version has some problem. I will send you guys the old version. Okay, so I think the new version has some problem. Okay, so if you have a problem with UAV box, for some students, if you have problem with UAV box, you tell Jalal. Okay, Jalal can promote the folder privilege. Okay, just ask him to use a link that can share with you even in external to UAV. Okay, we are using internal UAV account, but if some of you may not be active with bot, okay, try to contact Jalal and let him elevate the privilege. That will solve the problem. It's okay. Or if you haven't received the email yet, ask Jalal. Okay, just email him and he will handle this. Okay, thank you.
So yeah, we do have a folder over here at Auburn. It's just got the images. Is that all we need, or is there a CSV that we also need?
Yeah, just the images. Okay, CSV is what you do. That's what I mean. Right. You type these, you add a class and you type these types in there, and then you can annotate them. Okay, and choose the right class. Okay, and then you export the CSV. It's okay.
Yeah, it's okay.
Yeah, does this make sense? So so for example, so there are several things. One is called the ping. Okay, ping is this kind of thing, right? So you will see that this ping actually cross the thread, right? So the screw thread, right? But you have to do this because this polygon only allows you to do something like inside the polygon, it belongs to the ping. Okay, right? So outside the polygon, it does not belong to the ping, right? In that case, so if you say, hey, this is the part, it belongs to pings, right? So you have to do this. Okay, there's some overlap, unfortunately. Okay, and this is a thread. Okay, this is a nut. Okay, this is the head of the screw. Okay, this is the thread of the screw. This is a nut that locks it. Okay, this is a pin. Okay, and it's not easy to handle this, so you need to. This is another pin. Okay, you need to. Oh, I should not change. So that's why you will have some time to get familiar with that. I think the new version is not stable. I will send the old version as a zip file to you guys, okay, so you can play with it, okay? Because there are so many objects, the version is not stable, that's good now, okay? And I think these are the basic stuff. And you will have this pin to lock the screw. And I think there's something else. So let me just look at it. Okay. So if initially it's not a radio already, just choose radio. Okay, if you load this example. Otherwise, you can first load the example, get those labels, and then work on your image. Finally, remove this example image and export your system. That's good. Okay. So here, so nut pin. Oh, washer. There's a washer. Right. So what is washer? Let me see. I'm not sure whether we have the washer here, by the way.
I have one question.
Yeah.
Yeah, it's written that the grades are given based on the percentage of missed objects. Means what can be the missed object?
Oh, so it's like our error function. If you have 10, you miss 2, then you get 8. Okay. It's okay.
Sorry.
So a percentage. It's percentage. If we expect you to
that
have.
Means missed object means suppose I missed the 41 or 45. Is that the things?
If you have 100 objects, you miss 20, you get 80 points. Okay. In 100. Yeah. If you have 100 objects, you miss 23, you get 77. It's okay.
Okay.
Yeah, that's what we mean. But
so you'd much rather have.
How many annotations
we
need?
Too many.
Actually, it's really what is in front of you. We will not be so strict, but hopefully you can mark as many as possible. Okay, if you mark more, there will be some actually bonus. I forgot the formula to calculate that, but we have a formula for that. Okay, if you miss one.
What's the upper limit then?
Sorry, is there any minimum requirement that the objects can be annotated?
What?
Is there any minimum?
Usually you will never have more than 100 objects. Okay.
We can do it like as many as possible, right?
What?
We can do as many as possible, right?
Yeah, you can do as many as possible to be safe. But this is an extreme example. This is 80 something, right? So usually you.
But how can you calculate the percentage? Sorry.
What?
How can you calculate the percentage of the object missed if we can do as many as?
Let me tell you. So for example, if you look at the annotation file, It's a CSV file, okay? We have a formula for that. So basically, you will see how many lines of annotation you have, 90 of them, okay? Right.
Okay.
Yeah, this is basically how it records the annotation, what's the column, right? If you have 90 and we expect 100, then you get 90%, okay?
Okay.
Yeah.
Professor, I'd like to know what is the takeaway from this assignment. I'm just curious.
Oh, it's mainly to prepare you for those kind of tools, right? So this is an annotation tool, okay? And at the end of the semester, we will have final project where you can choose from this tool, okay? To do object detection, right?
Okay, okay, Professor.
Yeah, so like the Mascasian we show at the beginning of the course, okay? And by that time, because all of you contribute some annotations, collectively there will be enough data for training, okay?
Got it.
Otherwise, if you only have 10, you cannot train. Okay.
Oh, this assignment.
What?
The due date.
Due date is all here. Okay. I mean, so basically there are two things you need to read carefully. Okay. So one is this file. Okay. One is this file tutorial. Another is this announcement. Let's say the due date is this. Okay.
Okay. Thank you.
Right. And also this slide, which I will try to go through because I think the time is almost up. Okay. So let me go through this. And by the way, I will send this old version to you guys because the new version I just found out it doesn't work well. Okay. And one thing is that if you let's say you work on something in the middle, right? So you annotate something in the middle. You don't want to separate the data and annotation. What you can do is you can save a product. And next time you can load the product back. Okay. This is like your workspace, including both file and annotation. But when you finish, ultimately, you just upload your annotation. That's good enough. It's okay? And sometimes, if you forget to click the class, there will be problems, right? You need to go back to the CSV file to fix it. Otherwise, it will not work, okay? So in those cases, you before you submit, it's better if you can load all your files and then you can import your CSV and see whether it works properly. If not, you need to fix. You need to edit the file. Okay, go back to the file. Maybe sometimes, let me give you a thing.
So we just need to annotate the demo image that's on the assignment instructions?
Yeah, exactly. So what you do is you add all those files here, 10 files here, and then you set the class labels, right? And with radio, and then you polygon and click what's that, click what's
Well, are we annotating all 10 images or just
all 10 images? Yeah.
All 10, okay.
Yeah, and then finally you export a CSV, okay?
Professor, could you clarify how many annotations you want per image? Around 100 maybe, or less per
Some
image?
images only 10 or 20 or even 5. Some images maybe 80. There's no more than 100 as far as I know, okay? Yeah.
Thank
you. If you're lucky, maybe you only have 10 or something. Okay? If you're not lucky, because we randomly shuffle the images, okay? Then you probably have 80. That example is extreme example, right? And
sorry, are we going to have a separate CSV file for each image? Or?
no, you will have all the CSV file together for one image. If you look at, let me see where the CSV file.
I mean, we have 10 images, so we have 10 CSV files.
Just one moment. I think I need to use a text editor to open. Okay. This is comma separated. This is a table head. This is the file name. Okay, etc. Okay. This is 91, the first object. 0. Okay. This is the second object. Okay. 1. Okay. Keep in mind, this 0, 1 will be 1 less than what is shown on the image. Okay. If you remember what we show on the image, it starts from 1 to 3. Okay. If you want to come back and find it in the line, okay, you need to go 1 less. Actually, it's easier to open use Excel. Okay, so this is probably easy. If in Excel, you double click this, it will basically expand the column for you. Okay, this is Excel stuff for you. Okay, so you will have the file name. Okay, so in our example, all 90 are for this file. Okay, if you have 10 objects, 10 images, this will be another file name. Okay, And this will be like maybe 20, 0, 21. It's okay? 22. Latif, it's okay?
Yes, thank you.
Yeah, you only have one Excel file, okay? I mean the same, right? This is the total count. This is which one, okay? In the image, you see that these are 44, 43, right? So if in the image you find 43 has a problem, you come and fix 42, not 43, okay? Well, in the image, somehow they start from 1, but in the file, they start from 2, okay? And these are the polygon coordinates. That's why it knows where to plot, okay, in the software. And all of them are polygons. And what can be problematic is maybe finally after you plot the polygon, you forget to write the class, right? And this will cause problem. Something like if you pass this CSV file, you find this is undefined, right? All the rest, it will not read it, okay? Then you will see a lot of things missing. Come here and search for like something undefined and then fix this later according to the image, right? So for example, here, if you see 67, right? Go back to the software and find the 68, right? And see what it is. Maybe it's a nut. And come back and fix this to nut, okay? Then problem solved. It's okay? This is a common error that you might see, okay? But again, keep in mind that you have two parts. One is file, one is annotation, right? So this is the annotation, this is load file. But you don't want to do that, you can save project, okay? Let's say if you annotate 2 files and then you want to take a launch, right? So then you save the project somewhere, okay? And next time you load the project, continue working on it, okay? This is a surface work because annotation file sometimes after you save, you load it because of the undefined kind of thing. That could be problem, okay? This is not mentioned in our manual. By that time, we are not saying this. It's like you finish all of them, okay? That's a bit risky, okay? Use the save the project and then load, okay? It will have both the file and the annotations, the current status. And when you finish, you export, okay? And we will send you this version of the VIA because the new VIA version has some problem, okay? I believe in our website, you can go to historical archived version and still find that version, but we will just share it with you guys. Okay? Sometimes you update the software, you have new problems. Okay? And so that's pretty much it. Let's quickly go through. Let's quickly go through the. I think we don't have time for the next one. Let's quickly go through the slides. That we the instruction for the assignment. Okay. And then that's the end of this. Okay, this class. Yeah, so this is VIA annotation, right? The purpose of the project is how to use VIA because it's a general annotation tool, right? With 10 images, you kind of know this tool, how to use it, and you be able to use it professionally. Later for your own project, let's say medical imaging, right? So you highlight a cancer, right? Tumor, okay, pileup, so it's cancer, right? So you can easily use it, right? Okay, it's very general. It's just a coordinate image. Where is this stuff, right? So it's actually generally applicable, and the VIA format is actually compatible with a lot of deep learning software. Okay, and yeah, so this again, the last purpose is really once all of you have all the annotations, we will, of course, the tier will pick out some low quality ones and then assemble a data set that all of you can use to train, right? Then later when you test later, you will know which part is which, right? You will recognize it, okay? So the real purpose of the project is detect an object to fix, right? It's loose, right? So this will be a second task, which we will not look at in this course, okay? So basically, we can do multitask learning. Let's say, hey, you cross out somewhere you have a problem, right? But if you know the path, this will be even more obvious, right? So basically, it's a multitask learning. Okay. And so here we just have a simple task. Right? This missing nut. This is a ping, right? This is a ping miss. Okay. Then this is for another true purpose, right? But we first need to make sure the feature of high quality. We want to recognize the object. Okay. That will be probably the goal of this project for the final project. Okay. And here are the classes, right? So take these 5 classes as a ground truth. Okay. Just use head, thread, nut, ping, and washer. Don't use both. Okay. We want a consistent because finally we will concatenate those CSV files together, right? We don't want someone has a lowercase head, someone has uppercase head. Just use uppercase HEAD, right? Uppercase T, then HIA, right? And nut, ping, washer, all together, only these 5 classes, right? So what do they mean? just look at this line. You will know this is hat, okay, this is nut, and this is thread, okay. This is pin, this is washer, okay. Washer is usually combined with nut, right? You put on top of the nut, right? And here's a load the 10 files, okay, here. And then you will see these 10 files listed, right? And then expand this attribute, okay? And then what you do is you select radio, okay? And then in the radio option, you add all the classes, okay? The first thing is that you need to do this, right? So you say, hey, I should have a Y which is called plus, then you will have this, right? And then you choose radio, okay? And then you zoom in and annotate the object. How to zoom in, how to zoom out, just look at the other menu you have, okay? But the other menu has another set of class. Don't treat that, because that is the instruction for VIA, okay? This is the assignment requirement, okay? Use these 5 classes, okay? In the slides, not in the work. Okay? And so something will be looking like this, and then you can annotate the object, right? And keep in mind, this object here, let's say if you look at the object, this is 50, right? If you go to the annotation file, you should look for that file as 49 object, because it starts from 0. But in this annotation, it starts from 0, from 1, okay? And then you annotate, right? So these are steps. Okay, click the boundary points and press Enter key to finish. Right? So you click boundary and you press Enter on your keyboard. Then it's done. Okay, this is the polygon. It will close the last edge. Okay, from the beginning point to the end point. Okay, and then escape. You will deselect the object, and then you click inside the polygon. Must be inside, by the way. Okay, and then it will pop out a pop-up menu, and you choose the right class. Okay, if you strictly follow the steps, it will be easy. Right? So it's not easy to use if you randomly do it. Okay, so that's why we have the steps so clear. Right? And if you click the cross button, you can delete that. Okay, and the control plus, on Mac it's command plus and the minus to zoom in, zoom out. Okay, and then after you finish, you can export the annotation, right? And you can also import the annotation, but if you save the project, then there's not much point on doing that. Okay, and do keep the file. Okay, this is what you do so far, right? But if you save the project, it should be fine. Okay, if you want to be safe, you export the annotation, and in the meanwhile save the project. Okay, and so CSV or JSON, both are fine, but we will choose CSV, okay? Because it's easier, it's 1 line per object, right? So it's easier to aggregate, okay? So radio option, by default, it will be passed, okay? Because it doesn't really matter. So in the Excel file, it's just the class name, right? If you choose radio, it will go through all the classes and compile a list of options. Okay? Otherwise, it will just be a class name. And so if you continue annotation, you can use these steps. But again, you can also save the project and load it back. And you can, okay? And so here are what objects to annotate. Okay, so front side, especially front side, and 2 small objects can be loaded. Okay, usually big objects. Okay, not too small. On front, then you do that. Okay, and the more the better. Okay, but we will count the missing annotations you have, and we will cancel it. Okay, and check out our demo example. Okay, that's all for assignment 1. Any questions? Yeah, if you have no questions, that's the end of this class, and I will send the older version of the VIA feedback. Okay. Thank you, everyone, and yeah, I will be here for 2 more minutes. If you have any questions, just ask me. Okay. If not, after 2 minutes, no one asking me a question, I will just go off. Thank you.
Thank you, sir. I had one question. So
yeah,
for the heads and nuts, let's say if the annotations are kind of unbalanced, let's say there are more heads and nuts, but washers are very rare, pins are very rare, how would you adjust the model for that discrepancy?
So that's a model training issue. It's not the annotation issue, okay? That's right. You are handling the data side, okay? It's not a model side, okay? Yeah, if you have 10 nuts and just a 1 pin, just to do that, okay?
Thanks.
Later when training, you can sample, you oversample thing and undersample them. Okay.
I see. Thank you, sir.
Yeah, I see a lot of people. So we have two kind of people, right? One have UAV box with no problem. Another category just say, hey, you don't have the privilege for the account. I do see this kind of issue. Okay, so I don't know why. I cannot figure it out. So for example, I think for Sami, UAV box it works, but for Latif, it doesn't work. Okay, so we will elevate the privilege, not just within UAV. We allow everyone can access the folder. By that way, so everyone can access. So you will not have this issue. Okay, but you need to contact Jalal. I will tell Jalal again so that he can fix this. Okay.
Yeah, I still didn't have the privilege. I contacted Jalal this morning. And
so if you elevate this privilege, you don't need to log in. Okay.
yeah.
Anyone can download, right? Yeah, I will ask to elevate it. If you cannot access, you can also send the email to Jalal. Okay, he will elevate the privilege so that you can access it. It's okay?
Yes, thank you.
You're welcome.
He already fixed it. Thank you.
Yeah, I see one student haven't got the folder, so you can email Jalal and CC me, okay, and then we can follow you up, okay.
I just want to make sure I understand how to save our work as we work through the images. So just to make sure we would export the annotations as a CSV, and then when we want to go back to it, re-upload them later.
Oh, so you can export CSV and later you can import again, right? You improve those files
as we go.
Yeah, because you see the CSV has a file name and it has all the polygon shape, right? So basically it can map which file should go to which polygon. Okay. But during the annotation, do just save the project. Okay, don't use those kinds of things. At the end, you can export and import again to see whether it works. Okay. During the process, just save as the project. Sure.
Is there a required minimum for annotations per image?
Actually, it's by common sense, actually. For example, if you fly drone and you see, let's say you face transmission tower on the side, right? So then those parts on the side, you wanted them, right? On the opposite side, those very small ones at the bottom, you don't need them, okay? We will not be so strict, but try your best to annotate what you think makes sense.
Thanks.
Okay, you're welcome.
I have a question.
Yeah.
So I see the application, like in case of medical imaging or material sciences, you would have 3D images and you would have slices of all those images, like say brain scans. You'd have slices of the images containing voxels. And for suppose if a researcher in the lab is given this task of annotating these images, and how would you know if he made if he did a good job on
annotation? So this is annotation the human part, right? So you need to have a supervisor, like in our case a TA, to make sure.
You just cross check.
Yeah. So basically annotation is all on the annotator. As I said, if you are paying somebody and he's randomly give you any garbage.
Yeah.
And you get this thing, right? So machine learning is data driven. So basically, it's really how wide the quality is looking like. Right? It's just like what we see today, right? If your Y is noise, right, then you learn this. Right?
Yeah. Because there is no way you can say if he's doing the job or his kid is doing the job, because you would give an iPad and you give the.
Yeah, exactly. So we have the TA, right? So usually, if you have a company, or you are in a research lab, there should be some supervisor or some poster checking all the images, make sure they are.
Yeah.
But again, if it's your own research, let's say you yourself, you are annotating, right? So then you would.
Yeah, then it should be fine, but. mostly it's not the case, right? It would be only.
You can see that immediately, right? So if you
Yeah.
So this is not a difficult stuff.
Yeah.
Some people maybe there are 30, they missed 1 or 2. That's fine, right? So but you see everything is wrong, and or maybe 70% is wrong. Obviously, this guy's.
Yeah, the problem in this case is you would have many slices in the order of hundreds.
But if, let's say if you run with sample 10, you see all of them are doing good. Probably this guy is doing good. Okay?
Yeah, then you would know. Yeah.
Yeah, you cannot go through that.
Yeah.
But for the summit, we will go through everything. Okay. Yeah. But if you, let's say if you are doing processing, you cannot do that, right? You sample some and take a look.
Yeah. Yeah. All right.
Okay.
Thank you.
You're welcome. Yeah, and those models are robust, actually. If you miss some, they can still recognize them. Okay, later.
Mm-hmm. Yeah. Yeah, with the iterations, you would improve the.
Yeah, because those images also, like those kind of shape also appear in other images. See the other people annotate. Right, so finally, missing some is fine. Okay.
Yeah. All right. Thank you.
You're welcome.
Just wondering, can we get some TA hours in the evening? Yeah. The TA hours are during the day. You know, some of us are like working during the day. So is there any way?
Okay.
Is there any way you can assign some TA hours 5 o'clock?
We need to discuss this. If you have this special requirement, send all the students. If you have this requirement, send an email to me, and I will see how to handle that. Because for department officially we can only do 8 to 5 p.m. 8 a.m. to 5 p.m. Right? So after hours, they're not paid to do that. Right? But we can accommodate some. For example, if the TA, let's say, can do 1 hour in the morning and 1 hour in the night, we can consider that, right? So let's see how it can work out. Is okay?
Okay. Yeah. Thank you.
You're welcome. Okay, if you have no more questions, I will just offline. And if you have any question, you can send me email. Thank you. Oh, by the way, so next time we will take attendance. Okay, today we still skip the attendance.